Okay, so the question I picked is an HL chapter 2 question. It states that the values for the first three successive ionization energies for two elements X and Z are given. We are then given with element X and Z the first, second, third ionization energy values in kilojoules per mole for each element. Then the following question asks, it says, which pair of elements represents X and Z? So which elements are X and Z? We have to deduce that. So we're given with option A, lithium, beryllium, option B, lithium, carbon, C, beryllium, lithium, and D, beryllium, carbon. So first of all, we have to realize or analyze the patterns in these ionization energy values. So for Z, it's almost being doubled each time. So here it's almost double, and here it's almost double. But the value for Z, the first ionization value for Z right here, is bigger than the first ionization energy of X. So that will be explained later on. But then the second ionization energy of Z is lower than the second ionization energy of X. And the second ionization energy of X is almost 14 times the first ionization of X. Sorry, the second ionization energy of X is almost 14 times the first ionization energy of X. But then the third ionization energy of X is around maybe 1.5 times the second ionization energy of X as well. So the increasing pattern in X is not the same, so right here, is not the same as the increasing pattern in Z. The increasing pattern in Z is double each time, almost, but that pattern does not apply to X. So first we have to realize what is the first ionization energy, what is the second, and what is the third. And how does this ionization energy pattern occur in the periodic table? Okay, now generally, the general pattern of, or general trend of ionization energy is that it increases as you go up a group, and it also increases as you go right through a period. That's the general trend of the first ionization energy. What is the first ionization energy? It's defined in the Oxford Study Guide as the first ionization energy of an element is defined as the energy required to remove one electron from an atom in the gas state. And obviously it's measured in kilojoules per mole. Okay, now this is the graph of the ionization energy of the first 20 elements of the periodic table. So these values right here are the ionization energy values of each element, and here it's the you could also put the atomic number as the x-axis because it says the first 20 elements, so here could be 20 and here it's 1. Okay, so what we can deduce in this graph is that there are almost 3 major decreases in this graph. We could see it from helium to lithium, from neon to Na, and from argon to potassium. Now, what these red lines that I have just drew in the graph represents is that we have to look at the electron configuration of these atoms. What we can also deduce is that in the for example, this red line right here, let's look at the atoms in the periodic table. So we have helium over there and lithium over here. So helium is at the very, very, very right side of the periodic table, and then lithium is also a new period on the very left side of the periodic table. So lithium is in group 1, while helium is in group 18. But the reason why helium has the highest energy in this graph is because helium has 2 protons and 2 electrons. And with that in mind, the two electrons are in the lowest level and are held tightly by the two protons in the helium atom, which makes it pretty hard to remove the first electron because it's held tightly by the two protons. But for lithium, over here, it's at around 500 ionization energy value. This also gives us the approximation of 520 in the question. So we could tick off C and D. We are left with A and B. But then, to further explain the point of lithium being very low, is because the reason why lithium is in a very low area in this graph is because the third electron in lithium is at a higher level than the first two, which makes the first ionization energy. So for example, we have one electron right here and two electrons right here. The energy required to take away this electron is not so great because it's at a higher energy level than the first two right here. And these first two are not held but are tied together in the lowest energy. And as a non-scientific analogy, you could almost take this line right here as a barrier for these two electrons, because this first electron needs to be removed for these two to be removed, obviously. Furthermore, what we can deduce from this graph is that there's also a gradual increase from boron to nitrogen, aluminum to right there, and then potassium to the calcium ion, and also sulfur from argon. But to minimize repulsion of electrons, we could use the electron configuration quote-unquote graph, which states that in each level of S and P, so S has two electrons, and they're oppositely, or not oppositely, but they spin oppositely, and they tend to repel each other. But when the orbitals of the same energy, so S and P, which are degenerate, when they are filled, the electrons will go singly into each orbital first before they pair up to minimize repulsion. So for example, when you draw this quote-unquote graph, for P, you wouldn't draw it like that to fill it up. What you would do is that you would fill in each box, in this case, first, and then go back to fill the empty spaces. And this is like a physical analogy of the degenerate electron repulsion ideology for ionization energies. So to further explain the point of this increase right here, because boron and nitrogen, as seen in the periodic table, they're in different groups, but they're in the same energy level, which is P. So just like that. And the theory or the ideology I've just explained explains why there's a regular increase in the first ionization energies going from boron to nitrogen, as the 3 2p orbitals, so right here, are being filled up or by one electron. So boron is a 2p1 because it's right there, so it's going to be like that. However, carbon is going to be a 2p2, and we're not going to draw one right there because of the reason I've just explained earlier. And then nitrogen is going to have a third electron right there. But then we could also realize is that there's a slight decrease between nitrogen and oxygen, and then from magnesium to aluminum. So why this happens is that one of the 2p orbitals, so one of the orbitals right here, so one of these orbitals gains a second electron before a regular increase again, so right there. So what happens is that between nitrogen and oxygen, nitrogen is a 2p3, so it's going back to the first orbital. But for oxygen, it's a 2p4, same as to nitrogen, but then the second orbital is has a extra electron in it. So therefore, because oxygen has a extra electron in the 2p2 or a 2p4 orbital, or in the second box I've just drawn, that's why oxygen has a higher ionization energy for N. And when we look at helium and lithium, this massive decrease in the first red line, it's because helium has a lower orbital level than lithium, because lithium has an S. However, helium is a P. Also, neon and Na, or sodium, the other red line, neon has a 2p6, while sodium has a 2p6 plus a 3s2, or a 3s1, sorry, because it's in a new group and a new orbital is being filled up. Again, argon and potassium, argon is at a 3p6, while potassium is at a 4s1 with a 3p6 orbital already being filled up. So now we have to deduce whether Z is beryllium or carbon. We look at the periodic table. Beryllium is right over there and carbon is right over there. Obviously, we're not going to look at this graph because it's not given to us in the data booklet, but the periodic table is. So anyways, beryllium has a 1s2, 2s2. So beryllium has a 2s2 orbital filled up already. It does not have a p, because the p block is over there, the s block is over there, and the d block is over here. And this is the f block. Now, carbon also has the 2s2, obviously with the 1, but that's not so relevant for now. Also has the 2s2, but it also has the 3s2, because it's second over here. So carbon has more electrons, also electrons at a higher energy level. So it's higher, so it's harder to remove. So the energy for carbon has to be greater than beryllium. Therefore, beryllium here and carbon over here, they do not satisfy, or beryllium specifically does not satisfy the first ionization energy given right over there. Because of these options being so easy to deduce from the periodic table, we don't really have to deduce second and third ionization energies. We could only look at the first and second. However, for carbon, since carbon has electrons in a new level or a higher level, the second ionization energy, which is the energy it takes to remove an electron from a +1 ion, which means, for example, the second ionization energy, it's not the energy it takes to remove two electrons together. It's the energy it takes to remove one electron from an ion or an atom that has already lost one electron. So the second ionization energy right over here, the 2350, is for carbon, because it has to be for carbon anyways, because carbon has a new energy level which is 3, and it's also a p. I've mistaken that, put it in a s, but it's a p. It's in a p orbital. So not only it's a new or a higher group, which means higher electrons or more electrons, it's also in a new orbital level, which satisfy the answer being B.